In this presentation, we will discuss airflow in a ducted HVAC system. High static pressure at the supply and return sides of the system may lead to poor airflow through the duct system, and also blower motor may draw too many amps and overheat. The incorrect duct size for the heating and air conditioning equipment installed is another issue. Use Manual J to ascertain the correct equipment size. Evaluate and modify the existing ducts to make sure the ducts will be able to handle the necessary airflow. We must understand the pressures in a ducted HVAC system. Static pressure, the resistance a cooling and heating unit faces when trying to push air through the ducts. It is an important factor in evaluating the performance of your HVAC unit. It is the root of many cooling and heating problems in ductwork. Velocity pressure, the pressure caused by air in motion. It is the velocity pressure that we feel when the wind blows. Velocity pressure cannot be measured directly. The easiest way to determine the flow velocity of air is to measure the velocity pressure in the duct with a pitot tube assembly connected to a manometer. Total pressure is the sum of static and velocity pressures. The drawing on the right shows static pressure in blue, which is equal in all directions. Velocity pressure is shown in red and is the direction of airflow. Knowing the static and velocity pressures allows the conversion of pressure to airspeed in feet per minute. It also allows the conversion of pressure to air quantity in cubic feet per minute. A pitot tube is a tube within a tube, an instrument used to measure static pressure, also used to measure total pressure. To measure total pressure, the airflow must go directly into the pitot tube in the direction of the flow. To measure static pressure, the air will enter the outer tube through the equally spaced openings. Air pressures are very low, so we cannot accurately measure the pressure in pounds per square inch. We measure air pressure in inches of water column. In round numbers, 1 pound per square inch equals 28 inches of water column. In the picture below, I have 1 square inch column of water, 2.31 feet tall, which is 1 pound per square inch. Therefore, 2.31 feet times 12 inches per foot equals 27.72 inches of water column. In this drawing, the correct method of measuring total pressure is shown. Note the airflow is moving directly into the inner tube of the pitot tube, which is connected to the manometer. In this drawing, the correct method of reading static pressure is shown. Note the airflow is moving directly into the outer tube of the pitot tube, which is connected to the manometer. In this drawing, the correct method of reading velocity pressure is shown. Note the airflow is moving directly into the outer and inner tubes of the pitot tube, which are connected to the manometer. We are now able to convert velocity pressure to velocity in feet per minute, which is the speed of the air. For this example, assume the manometer reads a velocity pressure of 0.025 inches of water column. The formula for converting is velocity in feet per minute is equal to 4,005 times the square root of the velocity pressure. A square root is a number multiplied by the same number. Therefore, the velocity in feet per minute is equal to 4,005 times the square root of 0.025. The square root of 0.025 is 0.1581, which can be found on most calculators or device apps. Velocity is now equal to 4,005 times 0.1581. Therefore, we now have the velocity in feet per minute of 633.19. Once we have determined the velocity, we must determine the airflow in cubic feet per minute. Assume a duct is 12 inches by 24 inches. In the previous slide, we calculated a velocity of 633.19 feet per minute. We must convert inches to feet. There are 144 square inches in 1 square foot. I showed 12 times 24 inches divided by 144 inches, which would equal 2 square feet. The formula is CFMs, cubic feet per minute, is equal to the area in square feet times the velocity in feet per minute. Therefore, the cubic feet per minute is equal to 2 square feet times 633.19 feet per minute. The conclusion comes to CFMs is equal to 1,266.38. External static pressure is the measurement of the duct system that the fan has to work against. It is the sum of the suction pressure and the discharge pressure created by the blower. To measure external static pressure, we use a manometer to read the pressure of the system before any coil and after the filter. In this example, we will show a reading of 0.5 inches of water column. Using the chart provided by the equipment manufacturer, we first identify the equipment. Next, we locate the reading of the manometer, draw a line straight down, and from the equipment, we locate the CFMs at this external static pressure. Note, if you change the speed, the external static pressure and the CFMs will change. Another method to determine the CFMs is to read the pressure drop across the evaporator coil. In this example, we are reading a pressure drop of 0.2 inches of water column on our manometer. Using the chart provided by the manufacturer, we locate the coil and find the pressure reading on the manometer. Looking across from the coil, we locate the CFMs. Note, this procedure should only be done with a wet, clean coil. Another method to determine the CFMs is to read the pressure drop across the filter. In this example, we are reading a pressure drop of 0.19 inches of water column on our manometer. Using the chart provided by the manufacturer, we locate the filter and find the pressure drop. Looking up from the pressure drop, we find the CFM. The temperature rise method is used to calculate CFMs for heat pumps with electric backup heat. The formula is cubic feet per minute is equal to the heating capacity in BTUs divided by 1.08 times the temperature difference. The first step to determine the CFMs is to have 100% of the backup heat on with no heat pump running. Next, we take the volt and amp readings. Now we take the temperature of the supply and return air. Note that the reading for the supply air must be out of sight of the heating elements to avoid the heating effects of radiant heat. The formula is CFMs is equal to BTUs divided by 1.08 times the temperature difference. Volts times amps equal watts. 1 watt is equal to 3.414 BTUs. The difference between the supply and return air is 100 minus 72, which equals 28. Filling in the numbers, we have CFM is equal to 230 times 45 times 3.414 divided by 1.08 times 28. Doing the math, we have 35,334.90 divided by 30.24, giving us a CFM equal to 1,168.48.